Good day everyone. Today I am going to discuss about chapter 5, which is the numerical solution to differential equations, and this is under the course numerical solution to civil engineering problems. And in this chapter I am going to discuss, aside from the analytical method, these are the methods used to define and solve for the value of x or y using numerical solutions to differential equations. So I think we should move forward in discussing this topic. So first, what are the topics that I will be discussing? We have two topics, which is the first one is the Euler's method, and the second one is the modified Euler's method, where under modified Euler's method we have Heun's method, and the second one is the midpoints method. I think we should move forward for the first topic, which is the Euler's method. So what is Euler's method? Euler's method is considered as the simplest way of performing numerical solution to a first-order ordinary differential equation, or ODE. Although this method is not accurate nor efficient to compare to other methods, it is useful for understanding the numerical process for ODE. So this is the most simple way on finding the value of x or y of a differential equation. And under the Euler's method, we consider a differential equation where it may be written in like this form or in a linear form, but we consider in numerical solutions that we must write the equation in this form, where we segregate dy and dx in the other side, and we segregate the function x and y in the other side through equating. And we let the initial condition of differential equation be x sub 0 and y sub 0 to solve for the new value of y n plus 1 of the ODE given a step size of h, or the increment, where the formula is y of n plus 1 is equals to y of n plus h, or the increment, times the function of x of n and y of n. So here are the formula to be utilized in this method, where y sub n plus 1 is equals to y sub n plus h times the function of x of n and y sub n. And the other one is to find the new value of x, which is xn plus 1 is equals to xn, or the initial value of x plus the increment h. So what is the y of n plus 1? It is the next value of the solution, and y of n is the current value of the solution, h is the increment or the step size in x, fxn and y sub n is the derivative or slopes of the function at the current point x of n and y sub n. And if the initial condition is x 0 is equals to y sub 0, then the iterative equations are xn plus 1 is equals to xn plus h. So I think we should move forward in solving a numerical solution using Excel. So I think we should move forward in solving an Excel problem, a differential equation problem using Excel and numerical solution as well. And this method is under Euler's method, and we are given a civil engineering problem which is timely, and it is really engineering approach. And where the problem is, a civil engineering firm is testing a new smart polymer support column designed to absorb seismic vibrations. In a controlled lab environment, the vertical deformation x or y in millimeters of the new polymer over time x s is modeled by secant x dy minus y plus 1 times dx is equals to 0, where y initial is equals to 0.5 millimeters and we must predict the deformation at x is equals to 50 seconds, where the increment size is 0.05. And before the material reaches its fatigue limit, predict the deformation where x is equals to 0.50 seconds. So first we must establish the h and put the original equation and establish the value of f, x, and y. So it's given here that the h is 0.05, and we must put here the value of 0.05 as the step size. And the original equation was also given in the problem, where secant x times dy minus y plus 1 dx is equals to 0. And for us to establish the value of f, x, and y, it is generally equated to dy over dx. So from this function, we must segregate dy and dx in the other side for us to be able the value of the function or the equation. So first, we must transpose y, the second term, which is the y plus 1 times dx to the other side, where the value will be secant x dy is equals to of y plus 1 dx. And if we divide both sides by dx and secant x, we can establish the new function of x, and we can segregate dy and dy over dx from the function itself, and we will establish y plus 1 over secant x. And we recall that 1 over secant x has a trigonometric identity, which is cosine x. And so we will establish that y plus 1 multiplied by cosine x. So this will be our function. And here are the table, and we must find the value of y, or the deformation, if we will estimate the time of 0.5 seconds. So in other terms, the problem is asking if what is the deformation, or y, if the x or the time is equals to 0.50 seconds. So here we will establish x of 0, y sub 0, x of 1, and y sub 1, and so on and so forth. And it is not given here the value of x of 0 as time rates. We must consider 0 as our starting time, and here it is given that the starting value of y is equals to 0.5 mm. And through Excel formula, we must find the value of xn plus 1 is equals to xn plus h. So we use equals. So x of n is the initial value, or the current value, and we must add it with the increment. For us to be able to not affected by the dragging, we must put dollar signs in it, and that's it. We have the value of x of 1, which is the 0.05, and we must establish here as well the value of y, where y sub n plus 1 is equals to y sub n, the current, plus the increment, which is 0.05. And don't forget to put a simple dollar sign between the formula, and we will multiply it by the function of x and y, which is y plus 1 of the current. Y is 0.05 plus 1 multiplied by cosine of x, which is 0. And for us to be sure, we must include several parentheses for us to be sure of our answers. And as we equate, so we have found the value, which is the 0.575. So upon consistency of the formula and the putting of dollar sign, I think we must consider dragging this until we find the value of 0.5, and the value or the answer for our question of finding the y in 0.5 seconds. So upon dragging this two, so we have found that the value of y within 0.5 seconds of a polymer support column designed to absorb seismic vibration is 1.40 millimeter within 0.5 seconds. So we establish that 0.5 50 seconds will result to 1.40 mm, or so yan. So at x value of 0.5, we found that 1.40. I think that's it. Thank you.